Welcome to the second part of the GIN Masterclass on urban heat islands. In this part, we will learn how to understand and manage urban heat from a human-centric people perspective. My name is Ariane Middel, and I'm an assistant professor of urban infrastructure in the School of Arts, Media, and Engineering at Arizona State University.
And I am Jennifer Vanos. I am also an assistant professor at Arizona State University, and I'm in the School of Sustainability. We also wanted to let you know that during our presentation, we have 2 interactive Mentimeter questions, so watch out for those.
The goal of this session is to understand the various metrics and variables that are used in the context of heat, people's exposure to heat, and outdoor thermal comfort. We will also cover the basics of thermal comfort. This includes how people exchange heat with the outer urban environment and which factors play a role in someone's personal comfort. It is not simply air temperature. We will see that there are a lot of other aspects that influence thermal comfort. We will illustrate those concepts with 4 case studies on heat mitigation through climate-sensitive design and wrap up with some of the competing goals and trade-offs that need to be considered when it comes to heat and thermal comfort. So let's get started. First of all, what is heat? In physics, heat is the form of energy that's transferred between 2 things that have different temperatures, and the energy flow goes from the object with the higher temperature to the one with the lower temperature. When we talk about heat in an urban climate context, heat can be described and measured using 3 specific metrics: air temperature, surface temperature, and radiant or mean radiant temperature. The most commonly used metric is air temperature, and it refers to how hot or cold the air is. When people talk about the weather, they usually mean air temperature. However, in some urban climate applications, the surface temperature can be relevant as well. Surface temperature is the temperature that you experience when you touch the surface. And then finally, there's mean radiant temperature, or short MRT. MRT quantifies the heat load on the human body. It is the sum of different kinds of radiation that hits the human body from all directions. This includes the long wave radiation that is emitted from hot surfaces, such as an asphalt parking lot in the summer that radiates heat at the human body. MRT also takes into account the shortwave radiation from the sun in places where there is no shade. MRT roughly equals air temperature in the shade, but in the sun, MRT can be 30 degrees higher than air temperature due to the added shortwave radiation, which makes a person feel much less comfortable when it's hot outside. MRT is the type of temperature that best describes how people experience heat when it is hot and dry outside. Now, how would you measure these different types of temperature? Part 1 of this webinar already covered the more common air and surface temperature metrics. Air temperature can be measured using stationary setups, such as a weather station that you would find at the airport. You could use smaller handheld sensors or vehicle traverses where thermocouples are attached to a moving car. Surface temperatures are commonly measured contactless using satellites that have thermal infrared sensors that essentially snap thermal images of parts of the Earth from space. On the ground, researchers use thermal cameras and infrared thermometers to get a more detailed distribution of surface temperatures in the urban environment. The mean radiant temperature can be measured in 2 different ways: through globe thermometers or so-called 6-directional setup. A globe thermometer has a temperature sensor that's inside a black globe. The lower left image on this slide shows a Kestrel heat stress meter, which has a hollow copper sphere that's painted matte black to absorb radiant heat with the temperature sensor inside. MRT can be calculated from the globe thermometer's temperature if the wind speed and air temperature are known. And globe thermometers come in various sizes and price ranges, and the cheapest version is a thermocouple in a gray ping pong ball. A more accurate but also more expensive way to measure mean radiant temperature is to use the 6-directional setup. This requires 3 net radiometers that measure the long wave and shortwave radiation in 6 directions. One example of such a setup is the MARDI card at Arizona State University, which is a mobile human biometeorological station that measures MRT on wheels. And we will meet MARDI in 2 of the case studies in a little while. With all the different types of heat metrics, the question that now comes up is, what temperature should we care about? And the answer is, we care about all 3. It really depends on the application and heat mitigation goal. For example, if you're interested in building energy use or quantifying the temperature difference between urban and rural areas, the air temperature is the right variable to use. If you would like to investigate intra-urban heat variability in the surface urban heat island that pertains to the skin temperature of urban surfaces, the surface temperature is your first metric of choice. It is also relevant for applications that investigate the touch scale. For example, if you would like to know how hot sun-exposed playground equipment gets in the summer. Finally, when it comes to thermal comfort and heat exposure of people, mean radiant temperature plays an important role. In dry, sunny areas such as Phoenix, it is the main driver of comfort, but there are many other variables in play when it comes to answering the question how people actually experience heat. Which leads us to the first interactive question of the day. What other factors besides air temperature and mean radiant temperature do you think impact thermal comfort?
Great, thank you, Ariana. Now we can discuss some of these factors that you would have answered with your Mentimeter response. So how do we personally experience the heat? One of our recent publications, led by Evan Kuris, defines personal heat exposure, or PHE, as the realized contact between a human and an indoor or outdoor environment in which the air temperature, radiative load, atmospheric moisture content, and air velocity collectively pose a risk of increases in body core temperature and/or the perceived discomfort. Of course, each person's experience will differ from the ambient temperature measured at the airport. And these experiences are impacted by behavioral and social factors, the built environment, differing outdoor and indoor temperatures, indoor heat exposure, and their own physiology. Feeling uncomfortable helps an individual change their personal behavior, if possible, and that'll help reduce the length of time they experience high heat loads and thus the potential increase of core body temperature. So to fully understand comfort and discomfort, we need to go back to the fundamentals of what is thermal comfort. Simply defined, thermal comfort is the condition of the mind that expresses satisfaction with the thermal environment. There are 4 physical factors that we already talked about on the previous slide, as well as behavioral factors of clothing and activity. Finally, probably the most difficult and variable aspects of thermal comfort include psychological factors, such as expectation, experience, and perception, among others, as well as personal characteristics such as sex, acclimatization, and age. Adaptive models have been developed to account for these psychological and personal factors. So when considering thermal comfort, there are 3 main conditions defined by Fanger in 1970. The first is that the body is in heat balance. Second, that sweat rate is within thermal comfort limits. Third, that our mean skin temperature is within comfort limits. There's also a fourth, which is the absence of local discomfort. For example, you may feel general comfort in your body overall, yet your feet or hands may be very cold, making you report feelings of discomfort. Overall, Fanger's objective was to produce a comfort equation requiring input of only the 6 basic parameters to calculate thermal comfort and to assess the 3 main conditions stated here. So how can we model outdoor heat exchange to assess thermal comfort? Well, by using those 6 basic parameters, we can approximate energy fluxes to and from the human body, such as evaporative heat loss and convective heat exchange, to determine how close to balance or to zero the body is, just like our bank balance. So we can ask, is there an energy surplus or an energy deficit when we sum up these factors? And from these rational models, we can also estimate skin temperature, sweat rate, and other outputs. In different climate types, such as a humid versus dry climate, the fluxes making up this energy budget may differ. For example, in a very dry climate, the evaporative heat loss is very high, yet convective heat loss can become a heat gain if the air becomes warmer than the skin temperature. Yet in humid climates, evaporative heat loss is much lower, limiting our ability to cool off. In all situations, by adding clothing, we increase the resistance of heat transfer from the body to the air, thus limiting cooling and making us feel warmer, which we must account for in these thermal comfort models. However, heat balance is a necessary but not sufficient condition for thermal comfort. We can also be uncomfortable due to sweating or high skin temperatures, which are both highly dependent on activity level. Early work shows that skin wetness, which is a ratio between required and maximum evaporation, is a good predictor of comfort. This value will increase when not all of the sweat can evaporate from our skin, making us feel more and more uncomfortable. Skin temperature is also a good predictor of comfort, yet looks different in the cold versus the heat. When we get to the warm side, the evaporation of sweat helps keep the skin cooler, thus making the increase in thermal sensation appear very steep. Thermal comfort and thermal sensation can be measured through surveys. In steady state, thermal comfort can simply be regarded as a lack of discomfort. And when one deviates from comfort in transient conditions, based on changing thermal load or activity, we will then want to measure a person's thermal sensation from hot to cold. An optimal environment would have an average rating of 0 or neutral. Studies that use these subjective scales can ask participants to rate their comfort and sensation, and then researchers often will then relate those responses to more objective thermal comfort models, as we're looking at here. So this is just an example of what we might be able to compare. When we look at subjective data, these are often referred to as a thermal sensation vote, TSV, or an actual thermal sensation, an ATS, or perception in research studies. And then we want to compare those subjective outputs to more objective outputs using models. So some examples of models are the PET, the UTCI, the PMB, Comfort model, among others. For example, using this 9-point scale, the PET would expect someone to be neutral when the physiological equivalent temperature is between 18 and 23 degrees Celsius. That's not air temperature, that's the PET. While many other models can be used, but they may use different scales or units based on how they were developed and why they were developed. In general, one hopes for a strong relationship if they're doing a study between predicted and actual thermal sensation. One example study led by Ariane and her team was completed in Phoenix, Arizona, using the PET, where they found a strong relationship between the mean actual thermal sensation vote and the modeled PET across all seasons. The neutral PET across these seasons, in this case, was 28.6 degrees Celsius. This neutral PET may differ from location to location due to acclimatization, expectations, experience, population type, age, among other factors. This study also quantified the impact of shade on thermal comfort, a very important aspect of urban design for thermal comfort in the heat.
In the second half of this presentation, let's now look at some specific case studies that investigate further how to understand and manage heat. There are broadly 3 different approaches to heat mitigation. The first approach involves green infrastructure. Vegetation cools the environment through evapotranspiration, and trees provide shade, which reduces the radiant heat load on the human body and the surface temperatures underneath the tree canopy. The second heat mitigation approach changes the thermal properties of materials that can be found in cities. For example, changing the color of roofs and pavement to a lighter, more reflective color will reduce the amount of heat that is stored in the urban fabric because the energy from the sun is reflected back into the atmosphere. And then finally, the third heat mitigation strategy that is probably the most difficult to implement is changing the urban form. The way we design buildings and how we arrange them impacts airflow, temperatures, the amount of shade that's available, and so on. Changes in urban form can usually only be achieved over time because it requires redevelopment, so this heat mitigation strategy involves a little bit of planning. The first case study I would like to present addresses shade availability in cities. Municipalities around the world have recognized the importance of shade to reduce heat stress, and they adopted urban forestry plans with ambitious canopy goals. Oftentimes, though, the implementation of those plans is difficult because of maintenance issues, water use concerns, and infrastructure challenges. Engineered systems such as underground water utilities, communication cables, and overhead power lines stand in direct competition for limited space in the city's right-of-way. This case study was conducted in collaboration with the city of Tempe in Arizona. We used the MARDI cart to measure the performance of various shade types, from lightweight structures such as umbrellas, shade sails, and pergolas, to shade from urban forms such as awnings and overhangs, and then shade from buildings, and then finally shade from various tree species. We compared all of those shaded locations to sun-exposed sites that were not shaded at all. We measured all of these shade types during 3 times of day, which is at solar noon when the sun is highest in the sky, in the afternoon when air temperature is close to its peak, and then right after sunset. None of the shade types affected air temperature significantly, but mean radiant temperature varied as much as 50 degrees Celsius between measurements. Comparing the 3 shade categories, lightweight structures, natural shade, and shade from urban form, it is evident that all shade is great and significantly reduces MRT during the day, but urban form is most effective in providing shade, followed by trees and engineered structures. So based on these observations, we then developed characteristic shade performance curves that illustrate how mean radiant temperature changes over the course of the day for each shade type. And this will inform the City of Tempe's design guidelines towards using the right shade in the right place and will help with active shade management in the city.
Now I will talk about a case study in which we looked at the impact of misters for evaporative cooling in a hot, dry climate, which again was in Phoenix or Tempe, Arizona. So the goal of this case study was first to quantify the influence of evaporative misters on the thermal environment in outdoor restaurants in both the sun and shade, and second, to understand business managers' motivations to use misters. Results showed that misters improve thermal comfort across all days, all sites, and all exposure conditions, and was most improved using mist plus shade, where the PET and the UTCI were significantly reduced by 15.5 degrees Celsius and 9.7 degrees Celsius, respectively. Business managers also identified customer comfort and increased seating capacity as the principal factors for mister use. While this case study demonstrates value in outdoor misting in hot and dry climates, additional work is needed to more fully evaluate trade-offs between cost, water use, and comfort with continued urban growth. A third case study we wanted to share is where we modeled spectators' thermal comfort at the original Tokyo 2020 marathon course, which has since been moved to Sapporo due to concerns of heat. However, in this study, we used sky view factors modeled along the streets by Ariane and Middel, plus a full suite of mobile weather data. And we were able to complete heat balance modeling of the spectators to identify where they would be the most uncomfortable along the race course at the specific time of day during which the races would be ran. With this data, we were also able to make recommendations to improve the microscale conditions for the spectators and, of course, the runners.
The fourth case study highlights a fairly new heat mitigation strategy, cool pavement. The idea is to increase the albedo or reflectivity of asphalt roads by coating them with a lighter color to reflect the sun's energy back into the atmosphere instead of storing it in the dark asphalt. By reducing the surface temperature, the hope is that the air above the asphalt will not heat up as much, which then reduces the urban heat island at night. For this case study, we actually need to investigate all 3 heat metrics for comprehensive analysis. So this is an ongoing project with the city of Phoenix. Last year, the city coated asphalt roads in 8 neighborhoods with Cool Seal, a highly reflective coating. And to assess the impact on the thermal environment, we conducted vehicle traverses last summer to measure the air temperature distribution in those neighborhoods. And we also placed eye buttons inside the asphalt to measure the in-ground temperature, which is important for asphalt degradation. We also did helicopter overflights to take thermal images of the surface temperature distribution in the neighborhoods. And we took MARDI out for a stroll to measure mean radiant temperature on the road and adjacent sidewalks. Over the course of a year, We will take spectrometer readings every month to monitor the reflectivity of the pavement. We are currently in the process of developing surveys that will be sent out to residents to ask what they think about the new look of their streets. The study is still ongoing, so we won't be able to share results with you yet, but this is to demonstrate that all of the heat metrics are important for a holistic analysis of heat mitigation strategies. Now, to end the case study section, we would like to ask another question, and we would like to know, what do you think, what % of downtown city land on average is used for vehicles in the United States? That includes parking lots, roads, and any other paved surfaces. So with any heat mitigation strategies, there are always competing goals and trade-offs that need to be considered. So there's no silver bullet and no one size fits all heat mitigation strategy, unfortunately. If you increase the amount of vegetation, which provides cooling through shade and evapotranspiration, you also increase the amount of water that needs to be used for irrigation, especially if you're in desert environments such as Phoenix. If you increase shade during the day to increase thermal comfort, you may actually end up trapping the long wave radiation in the evening, and there will be some heat retention at night. So these are things to consider when you provide shade. And then finally, if you decide to increase the reflectivity of your surfaces on the pavement, on your roads, that will be really great to reduce the surface temperature, but then it may also at the same time increase the mean radiant temperature. So there's really no one size fits all solution, and always depends on the context and your heat mitigation goals.
So as a way to try to summarize that, we have a conceptual working diagram to think about these considerations and how to consider what's modifiable and non-modifiable, and what's extrinsic to a person or intrinsic to a person. So this is just a different way that we can look at these competing trade-offs, and then also account for the characteristics that we should consider when trying to model or assess thermal comfort. So this conceptual grid helps us to view and weigh such factors. For example, in a thermal comfort study, we must of course consider the climate zone, which is non-modifiable. Yet we can focus on the micro scale where we have opportunities to modify conditions such as wind and radiation, which are much easier to modify through design than air temperature and humidity. If we go to the y-axis, we can look at factors that are either intrinsic to a person or extrinsic to a person that will affect their thermal perception. However, those that are extrinsic to a person cannot really be modified, and those that are intrinsic to a person can be modified, especially if we're in this bottom right corner. So we can think about modification of our clothing, exercise intensity, and fitness, or people's experience, all of which affect their thermal comfort as well as their perception. However, we cannot modify pre-existing illness, their sex, their age, certain body characteristics, or if they're taking medication, which will also affect their thermal comfort. So it's very valuable to think about these in ways and trade-offs. And of course, the location of these will differ depending on the study and the person you're working with and the city you're working within. So with that, we'd like to wrap up and conclude and just summarize some of the main points made here. So the urban infrastructure can increase heat exposure, as was also discussed in part 1 on urban heat islands. And it can also mitigate heat through vegetation, urban form, and materials that Ariane outlined. Sensors and models can help quantify those impacts. And the type of metric is an important consideration. Individual thermal comfort is complex and highly individualized. It's important to understand the model used for thermal comfort as well. Finally, there's no one size fits all for designing thermally comfortable spaces. And that's not just for the way we design it in a city with form and function, but also thinking about what people will be using that space. So those spaces should be responsible to the needs of their users and be climate specific. So with that, we'd like to thank everyone for listening and for giving us this opportunity especially the Global Heat Health Information Network, Hunter, Julie, and Joy, for giving us this opportunity.
I'd like to second that, and thank you so much for your for tuning in, and we're now happy to take any questions.